All right, this is the second part of Section 8.4. This will be scheduled for Tuesday, which is the 27th. Yeah, 27th. So Tuesday, October 27. 8.4 is a little bit of a longer section. Of course, we're looking at apportionment. Am I represented? And so that'll be the main thing that we're looking at here, second part of it. Just to refresh your memory what happened before, we had the apportionment that tried to seek fair distribution of votes based on the population. And like currently, there's one representative in Congress, House of Representatives, for around every 700,000 people. And that would be the perfect way of representing. However, there are certain anomalies that occur. If you're close to getting that second vote, like we mentioned in Montana, your district could swell to over 1 million, but it isn't quite enough to get to the edge where you could get 2 votes. And there are several different ways that we can discuss as to how they are allocated. So we'll do that somewhat today. But the Alabama paradox is something we finished with last time, and I did want to talk about it a little bit here. We had Alabama's fractional part when we had 299 members. There was some way, there's, I guess, a dispute of how to calculate how many people would go in the House of Representatives. So it was between 299 and 300. The book does not go into that, but they do mention what happens with new states. Sometimes they've added votes to the House of Representatives, and sometimes they haven't. They just redistribute. So it just depends on the mood of the Congress at the time. There's nothing in the Constitution about that. So there is some dispute or some, disagreement as to how many votes would be. So the clerk there was fiddling with the numbers by hand, I'm sure, back then. And Alabama's fractional part. Now you can look in the book or look at the prior lecture to see what the actual distribution of the delegates was. But before, Alabama edged out Illinois. But then when you bring it up to 300 members, they all boost a little bit proportionally, an extra, third of a percent or something like that. And a bigger state will just get a little bit more because it has more weight. And so Illinois swelled up to 0.702 in its fractional part, but Alabama, being a smaller state, lagged behind and only had 0.671. So it ironically fell down according to Hamilton's method, which was being used. And Hamilton's method actually shorted Alabama some of that, even though the House had grown or potentially would grow. And I guess they were leaning on going from 299 to 300. So Alabama was quite upset about this. From parts 2 and 3, we just see here, and we're just tying up the loose ends of what we did last time. Increasing the number of seats changes the fractional parts. Well, that's obvious. Of course it's going to change. And almost always there's fractional parts. It's virtually impossible to have 0.0000. I guess it could happen, but odds are like 1,000,000 to 1, and it just never happens. So there's going to be a fractional part. And Hamilton, of course, ranked the fractional parts. And typically, most of the time, the ones that got high fractional parts would get the extra seat, and the ones with the lower ones wouldn't. But sometimes there were discrepancies, as we talked about before. But Hamilton's method allocated leftover seats according to higher fractional parts, and so because of this sway, Alabama did lose a seat, and Illinois did gain a seat based on this, and obviously they were not happy. But there are other paradoxes that are quite similar to this. And this one we didn't really talk about new states in particular, but there's a new states paradox where problems arise because of new states joining the United States. And they do mention in the book that when they added in an extra couple of them, I don't have the page turned to it right now, but there was some shifting. They were all thinking, there's only a couple more allocated votes to come along, and everybody else will just stay put. But no, somebody actually lost one, and then somebody got 3 or something along those lines. You can find that in the book. This, of course, does not expect to cover everything in the book, so there's a lot of extra information. Plus, I have another resource that I'm going to try to exploit, especially in the next lecture. A little glare here, can't see what I'm reading here. So we're getting into 8.4 and various things, and adjusting the divisor and Jefferson's method, Hamilton's method, and all that kind of thing. It does say that back in 1876, probably a little-known president, Rutherford B. Hayes, won. Samuel Tilden was a close second, another person that's in the history books, of course. And Tilden would have won if Hamilton's method had been used. At that point, they'd gone away from Hamilton's method. It's not clear here exactly which method they used at this point, but Hamilton would have given it to Tilden. So it would have been actual change in presidency using a different method. So yeah, you might think that this is only make a couple of votes difference, but sometimes that's all it takes. After all, in the year 2000, Florida was won by a candidate by only 500 votes. And Florida had a lot of electoral votes, so every vote does count. And that, though, by the way, those electoral votes did give the election to Bush back in 2000, even though Gore did have slightly more of a popular vote than Bush did. Well, anyway, let's go into this divisor methods besides Jefferson and Hamilton. They do mention Jefferson. And one that we've actually looked at before. We have these adjusted divisor methods. And of course, Jefferson does the dividing part. Let me get this pen back on. They turn themselves off very, very quickly. I can't seem to get it to go now. Where's my other pen? Let's try that one. And yeah, I'm trying to circle Jefferson, but it doesn't want to let me do it. So there we go. Jefferson's method. Round down, but not less than 1. Yeah, you can't get down to 0 votes. So yeah, round down until you get to 1, then you don't go any lower than that. That seems kind of obvious, but there have been some times where the 0 shows up, and so you don't want to completely gyp a state. But anyway, you find the quota. That's what would be in a perfect world, how many votes would lead towards a House of Representatives, which is quite similar to Electoral College, of course. And so Jefferson said round down. But Adams, he's a famous president, the second president of the United States, succeeded George Washington. He said round up, almost the same method, but to round up. How about that? And then Webster, believe it or not, we've seen this one before. This is just sort of the natural rounding. And frankly, this is probably my favorite, just the nearest whole number. Up if it's 0.05 or greater, and down if it's otherwise. So that's the typical rounding rules. We actually tried that in the very first example. I didn't have a name attached to that yet, but this is the more typical one. And this one, by the way, does hit the sweet spots pretty well. If you need 32 votes, it'll probably give you 32 votes. There won't be too much of an overage to take care of. Now, it's not perfect. There will still be one, but it's also been shown to be the least biased method, too. Well, anyway, we'll get into a little bit more of that later. If the sum from step 3 is larger than the size of the house, you increase the divisor. So in other words, if you're giving away too many votes, you have to increase the divisor and divide by a bigger number so it chops it down to size. We've already done that with Jefferson. And if the sum is too small, that is, we still have more to give away, which is what Hamilton always does, it seems, then you decrease the divisor, so you're getting bigger chunks as you decrease the divisor, and then you can repeat the steps until they don't really allocate it based on rounded decimals. They just want to change the divisor and then hope it comes out clean. And the book does demonstrate there's a wide range of numbers for which it works, and there is an algebraic formula that can be used. But they said, for all intents and purposes, and especially back then, they just use trial and error, and it doesn't usually take very long to get to a perfect number. Anyway, you find the divisor that works, and it's very much like Jefferson, except we have a couple of different strategies. Well, according to the most recent census that's available, because the 2020 apparently has just ended, and the population for 4 selected states are as follows. Montana is on the list. It made the news recently. And in these particular 4 states, 32 seats in the House of Representatives were given. And that would be a very close analogy to the Electoral College. I believe all you'd have to do is just add 2 to each of these for the senators, and you would have, 2 times 4 is 8, 8 more, but plus 3, you have 40 in the Electoral College. Just keep it topical, because that's in the news a lot recently with politics. Okay, so we can calculate the ideal district size in each state's quota. So each state will get a quota, and we'll try to hit to it, and then keep 3 places beyond the decimal point. That's just bookkeeping. You could, let your calculator keep 10 decimal places. That really does not matter. But in showing your work, you should get in the habit of doing what the book says. And Jefferson's method has already been done, and Hamilton's method has already been done. So these have already kind of been done, although not for this particular example. But the new ones, especially Adams, that one will be brand new, and we've actually kind of looked at 5 without naming it. So let's just see how all of these can go as we run through these particular examples. Okay, so the ideal district size for these 4 And I'm not quite sure why they picked them. Montana and Alaska are two of the smallest states as far as population is concerned. Florida, I believe that's in the top four. California, Texas, New York, Florida. I know California is number one, and the others I can't remember, but I know those are the top four. West Virginia looks like kind of an average state. So they just sort of picked them because it looked good. And so they get the 32, and they find that's surprisingly accurate for the country. Maybe this is part of it because that's pretty much the same as if you took all 50 states, at least as of 2010, around 700,000 per. Notice back in the early 1800s, there's only about 35,000 per, 39,000 per. So yeah, the population has grown by quite a lot, and although the House has grown somewhat, now each representative is responsible on average for these many people. So if you're in a certain district, I think Ken Calvert is my representative in the south of Riverside area. But anyway, that part doesn't really matter. But everybody has a district unless you're in Washington, D.C., and then that's a separate topic. So anyway, they've gone ahead and found the quotas, and you can see them 1.4, 1.0, 26.9, 2.6. And I guess the reason they picked them because this number is really close to 1, and that number almost is rounded to 27, but not quite. So let's take a look at what Hamilton would do. Okay, Hamilton takes the quotas and rounds down. We've done Hamilton before. This is nothing terribly new. So the 1.4 is a 1, 1.0 is of course a 1, but this is the weird one. 26.9 stays at 26, and even West Virginia stays at 2. They're all rounded down. Let me get a sip of iced tea here. Okay, so we look at the fractional part of the quota and we rank them. They haven't gone out of their way to rank them. Sometimes they put them in boldface, although there was a mistake on one of those. The 0.909 is clearly the leader. 0.648 is the next one. And then 0.416, and then, of course, the one that's way behind. And since we have 2 seats to add, because there's 2 missing, 32 minus 2 equals 30. So you can just kind of think of that way. And so we've got to supply 2 of them, and that's why Florida and West Virginia get extra votes, so to speak. So now Florida's gone up to 27, and West Virginia is up to 3. Okay, very nice. That's Hamilton, of course. Let's take a look at Jefferson. Now, Jefferson apparently will give a little bit more to the big states, and that's basically how Jefferson was criticized, I suppose. And so anyway, the quota is rounded down, just like before, and the total is less than 32. So this part is exactly the same. All this part on back is exactly the same as before. None of that has changed at all. So what they decide to do, instead of adding in artificially the votes that could lead to an Alabama paradox or other types of paradoxes, we could decrease the divisor to 700,000 and try to round down. So they do, and they don't have the exact details. I thought I calculated them. I'm looking for them. Let me see if I can find them. I had a little bit of extra work that I'd done for this. And yeah, so if you take it down to 700,000, what we have here, I should have not marked it up, but this would be 1.42. I'll just put down 2 decimals, not enough room. 1.03. So they're almost the same as before. 27.0001 actually. That one just barely crawled over. I'll just say 0.00, and then 2.66. This light blue may not be quite as visible as I thought it would be. Well, anyway, the 1.42 becomes a 1. 1.03 becomes a 1. Now the 27.00 becomes the 27. And then the 2.66 stays the same. So essentially, we got an extra vote for Florida. They got 28, and West Virginia got 2. Let's take a look back here. Remember, back here, Florida got 27, and West Virginia got 3. So Hamilton seems to be helping out the smaller states on average. Jefferson, not so much. So that's, we'll talk about the Electoral College another time. But the Electoral College, of course, is famous for helping out the smaller states. Okay, so let's look at Adams' method. This is one we have not talked about before. This is a round up method. So that's the main thing. Okay, Try and get this thing working again. Yeah, sorry about these pens. They die so fast. I can't believe it. So anyway, we're going to round up on this, and there we go. The total is more than 32, so the divisor is adjusted higher to 750,000. So notice, since we round up, all the numbers just get extra ones. This is one higher than it used to be. It used to be like 1, 1, 26, 2. So let's take a look at that. 1, 1, 26, 2 on this column here. And now we're up 1 apparently for all of them. 2, 2, 27, and 3. But then it's too many. Adam will go on the high side because everything's rounded up. And now we have to decrease by a certain amount. We have to get rid of a couple of them. So we have to subtract 2 to get 2 of them out of there. So because our number is too high, we have to actually increase the divisor. That will then give us a lower number, and we can do that. And still round up, though. It's still a round up situation. It's just a different view. Okay, so Montana, well, I actually have some numbers here for Adam. And so here, Montana got to 1.3. I'll put down 3 decimals, a little bit more room here. 1.326. That rounds up to a 2. Here's a weird one, 0.926. That does round up to 1. So Alaska fell below the threshold as you increase the divider, anticipating more population growth, something like that. This is just another way to get close to the answer. 25.201, and then 2.480. All these numbers get rounded up. If there's anything at all showing up, they get rounded up. So the 1.3 goes to a 2, the 0.9 of course goes to a 1. It would have anyway, it's sort of a default. And then 25.2 goes to 26, 2.4 goes to 3. And yes, that one does hit the spot. We don't have to go any further. If we had missed it, we'd have to adjust it again. So because our number is too high, we have to increase the divisor, and that's a way of chopping it down. It's an inverse relationship. When you divide by a bigger number, the totals go down, and that's what we want to do. So we started off too high. We divide by a bigger number to bring it down to size, and that takes a little while to get used to sometimes. But let's take a look at Webster. To me, this is the most natural. This is just natural rounding, and we just round nearest whole number. You don't even have to make a big deal about this. It's just the typical rounding method. My favorite. You don't have to think about it as much. And here are the numbers. They divided by about 702,000. They included all the decimals they could. And so 1.4 rounds down to 1. 1.0, of course, rounds down to 1. 26.9 rounds to 27. 2.6 rounds to 3. Yeah, hit it. And that's going to hit it a lot of the time, but it will not hit it all of the time. There would still be accumulated decimal errors, especially when you get to 50 or 51 quantities, and that they will just tend to collect. And a lot of the time, surprisingly, even Webster's method does need a little adjusting. A little less likely, in fact, a lot less likely than the others. But it still might need some adjusting. It's just the way they collect are in random ways. That's what they call round-off error. So even Webster is not immune to that, although much less likely, I might add. So not only is it easier, it seems to be one that hits the spot that you're looking for much of the time. I'll just say much of the time. Now this is the method Huntington Hill that is used today. So this got the advantage of being currently used. So that's today's method. And it's interesting because it follows the steps of the other methods, but the divisor is found using a geometric mean. If n is the whole part of a quotient, to find the geometric mean, use the formula. In other words, we place our borderline, well, kind of like Webster, where it's 0.5 and above, you get it, and 0.499 and below, you don't get it. Except here, we set the bar somewhere in the 4s. Usually it's going to be 0.4 ... And it just depends on what n is. They have a little table as well. For example, if n was 50, you'd have the square root of 50 times 49, which is, I don't have that in front of me, but it's, about 7 or so. So let's take a look at some of the examples, and we'll show you what I mean. If I can try to get to the next table here. Huntington Hill. Okay, well, we don't have 50 on this chart, but let's just say that n equaled 1 for the first value. Then you have the square root of n times n plus 1 equaling the square root of, if n equals 1, you'd have 1 times 2, which is the square root of 2, which is a well-known number, 1.414, at least rounded to 3 decimals. So this would be the dividing line, not 0.4, not 0.5, but 0.414. Anything below it gets rounded down. Anything above this gets rounded up, and that's a rather generous one too. At 0.414 is the best one on the list. Of course, that means you have a very small list. Notice as we get bigger and bigger n's, the numbers start gliding up closer and closer to the 0.5s. Already we're up to a 0.488. So in the practice, this doesn't make too much difference. It just gives a slight edge, but it's been considered to be the most fair way. So right now it's the current method being used, but the book does say the expectations are that at some point it would be changed. Look at 30, and we're not even talking about 50. If you have this kind of thing, you've got 30.496. You may as well just say 30.5, but they did give a little bit of compensation. If you're close to the 0.5, good enough. And especially if you have a lower group, like a group of 4, then you can bend it back a little bit further, but not significantly so. In fact, to some people it just seems like a bit of a waste of time, but it does seem to be considered to be the fairest way, and that's how they apparently compromised. So that's how we could go. And so here we can take a look at an example here. It's also found in the book. Yes, we have the n's, and there's the number of seats. Okay, got it. So yeah, the lower numbers will be used a lot, especially for lower districts, and so Montana being very, very small. Okay, so let's take a look at what happened. The beginning part is exactly the same as before. So this part is no change, the first 2 columns. So yeah, you've got your 22.5 million for the 4 states, and yes, 32 votes, representatives are given for it. It could be electoral college votes, I suppose, but let's just keep it in the House of Representatives. And because we have n equals 1 here, we have the geometric mean from the prior table, one we actually calculated, as the square root of 2, 1.414. The 0.414 is what really matters. Well, actually, the 1 matters too, because look how close Montana was. This is a very good example. 1.416 just barely beat, barely greater than 1.414. So yeah, it gets 2. Montana's happy. Montana did used to have 2 representatives, and recently it's been down to 1, and they're saying largely because of undercounts. Rural and Native Americans are tougher to get at sometimes, so that's been a problem. They're trying to get an all-out effort to get them counted, but it just is met with mixed success. We'll see what happens with the census when the numbers come in. But anyway, that's what they got. Let's take a look at just the first try for sure. Alaska, the original quota, as we saw before, does not make it. It's the same value with the 1, so we are less than 1.414, so it stays at 1. Now, Florida will have little trouble beating it with a 0.9. 0.9 is almost sure going to round up. And so as you look at the table for the value of 26, there it is, 26.495, awfully close to 26.5. But we did give it a little bit of an edge. It didn't really matter here. It wasn't likely to matter, but the 0.9 almost made it a moot point anyway, but we are trying to develop the Huntington Hill method. And so that one does round up, quite not surprisingly at all. West Virginia had a 2.648. This is all old news. This is previous on that third column there. And so the Huntington Hill method, without breaking out the formula, that would be the square root of 2 times 3, which would be the square root of 6, which they're telling me here is 2.449. So in other words, 2.449 squared would be a number extremely close to 6, because of course that is rounded. So that's the number we're going to borrow from the table. And there it is, 2.449. And yeah, it wasn't that close a call. West Virginia rounded up. But then, trouble with Huntington Hill, as with all the methods actually, some more than others, it went a little too high. Went to 33. That's 1 more than we're supposed to be. So that's not too cool. So what they had to do is they had to decrease the divisor. So we decreased it down to 640,000. And then they have, for change, they actually put in the quota numbers to 3 decimal places. Let me get another sip of tea. So when you see it, the rounded quota, based on geometric mean, we're still using that, still gets rounded down. Not because of the generous geometric mean, but because we had to divide by a bigger number to chop the 33 down to size. In other words, 33 was too high for what we wanted. So you had to divide by a larger number to make up for it, larger NO period. And so we did. And they picked, actually a smaller number, sorry, divide by a smaller number, got that backwards. So we divided by 640,000, and this is just a number they picked. They could have picked 650,000. That's just one that they happened to pick. So all these numbers have dropped down, and the rounded quota based on the geometric mean, none of them are really very close. And so the same results except for Montana. Montana got back down to 1. Sorry, Montana. And then the others stayed the same. They maintained because they just, even though they slipped a little bit, but not very much. Alaska, 1.027, slipped down to 1.016. That's still real close to 1. And I'm pretty sure they would have gotten 1 no matter what. They wouldn't have gotten 0. So 32 is the result that they're looking for. Without breaking out a complicated formula, they just did a kind of a trial and error search, and on the first try they got something. And when you're only off by 1, it's not going to probably take very much to do it. And they say you use spreadsheets and everything, so you don't have to break out the calculator. So we do have some interesting looks at these and the different methods we had. And Florida's got a lot of votes. It's a little bit hard to read, so maybe I can just zoom this a little bit, and we can see all the different methods. Jefferson is Florida's favorite. Jefferson seems to favor the heavier states. So yeah, Jefferson gave it a little bit extra. Adams, on the other hand, quite the opposite. Adams was the one that gypped them a little bit, and everybody else kept them at 27. So yeah, Adams had them round up, but they were already pretty much rounded up, so it didn't really help Florida at all. Webster's method, well, it seems to be one that keeps it at 27. Let's take a look at West Virginia, though. West Virginia is almost unanimous, except for Jefferson. Jefferson actually stole something from West Virginia, so that's curious. So all the rest were 3, and West Virginia came out behind a little bit. Sometimes it's just the way the numbers break, and that's why the census is so important, because all it takes is just a 1,000 or so, and the districts can change, and everything else can change. Now, Montana was the one that's sitting on 1. It has been for quite a while. And it wants to get to 2, but it hasn't been counted well, and plus not enough people live there, even though it's a beautiful state, especially the western part of the state. And so Adams' method would have given it 2. The roundup method would have helped out Montana quite nicely, but all the others only give it 1. Let's slide this over. Alaska is just so small. They're getting the 1 no matter what. They're just not big enough, so no matter what method you use, Alaska's locked in at 1. So that's just the way that goes. Okay, so chapter summary that we can use as we get closer to the exam. Let me get back here. We have voting power does your vote count, and so as we looked at especially 8.1, don't need to have that stuff up. Okay, this is the first section, 8.1. Okay, the pens just don't work as well as I was hoping they would. So anyway, that's the first one. Voting power does your vote count. Coalitions, quotas, swing voters, all these keywords that should make some sense to you, especially if you've worked with them for a while. Banzhaf Power Index, Stanley Shubik Power Index, that's all from 8.1. And so, there we go. Yeah, I'm not sure why it's not. These pens are just ridiculous. Okay, so I'm not sure why it's not working. Anyway, 8.2, voting systems, choosing a winner. Plurality is certainly one way. That's an easy way. Top 2 runoff, elimination runoff, board account, Condorcet winner. All those are mentioned in 8.2. That was probably the heaviest of all was 8.2, I think, because there are a lot of little things going on. Fair division methods, that divide and choose, adjusted winner procedure. This mostly has to do with inheritances or dividing up a prize amongst several people in a family or something like that are figure they're all entitled to a certain share. And then, of course, apportionment with highlights being Hamilton, Jefferson. Those are the ones we saw the most. adjusted divisor methods, which is what Jefferson was doing, and then some of the others at the end were even doing. And the current one being used is Huntington Hill method. So that's how that goes. Remember that WebAssign is available now, and you should be checking that out and working on those. Take them seriously. Some of them are only multiple choice, and they're not going to take as long to do. But you should definitely take them seriously, because right now that's all I directly have for you to practice with on the tests. So please don't skip those. And if you do make a mistake, be sure to learn from them. I guess with a multiple choice, you get several attempts. A lot of people are going to get some pretty high scores on that. But the main thing is to continue those high scores onto the test. So, yeah, I'll be trying to find various examples that the book has gotten us into, and we can try to get to that sort of thing. So I was going to try to find another example here for us, and something that we had just talked about. Apportionment by Hamilton's method. Let's see if we had the north, east, south, west, and if I can get the pens to work. That's a big if. Let's see if I can get them to work. Push the button, and yeah, okay, finally. So if I blot out a certain area here, maybe I can work on something that follows 8.18 in your book. It's actually the Try It Yourself 8.18. You remember we had the north, east, west, and south. So let me kind of review. Sorry about my bad handwriting. I am writing at an angle here, which is a bit awkward. So north, east, west, and south, and the populations, I'll just refresh your memory. 3,900 for the north, 4,800 for the east, 18,000 for the west, and 3,300 for the south, for an even total of 30,000 overall. So now we're going to have 20 counselors. So what they call the ideal district size, ideal, and there are 4 districts here. District size, and that district, I guess, is by counselors. Yeah, so there's 20 counselors now. So we'll take the 30,000, divide by 20, and get to 1,500. So instead of 3,000 in the population per, we've got 1,500 because you've got 20 of these counselors. So I'll go ahead and say 20 counselors. I'm not sure if I'm spelling that correctly. That sounds interesting. Counselor with a U. Well, anyway, I'm not going to spend too much time on that. Solors, and it's like little representatives for a city. So what we can do now is to come up with Hamilton's method to apportion a total of 20 counselors. And so what we'll do is we'll go through and we'll find out where the quota is. And for north, east, west, and south, as I put down quota, we'll divide them out and we'll get completely different numbers. As we divide by the 1,500s, let's put down a little bit of work here. 3,900 divided by 1,500, you get twice as many. Your book will say that you had a quota of 1.3, but this is now up to 2.6. Let me put the heading of quota. That is a number with decimals that tells you how many representatives you should have. And so the question is, we know we're getting 2. What happens to the 0.6? And so we'll continue and divide by 1,500, not 3,000. So a little bit different example here. 4,800 divided by 1,500. That gives us something that's twice as big as before. Looks like we're getting a 3.2. That's supposed to be a 3, sorry. And then 18,000 divided by 1,500. And let's see, we can get from that a much bigger number before. It's actually 12.0. That is a 0, by the way. It went in exactly. A rare event. But these are nice round numbers. South, 3,300 divided by 1,500 gets us a 2.2. So let me get you the answer. So 3,300 divided by 1,500. Okay, so now we have our quotas. Question is, what do we do? This is Hamilton's method. So let me put down, I'll just circle Hamilton's method. So what they're going to do is round down. So I'll just say round down. And then we have a 2.6 going to a 2, a 3.2 going to a 3. 12.0 stays exactly at 12. Didn't have to be rounded. And then 2.2 gets down to a 2. So we add them all up and see what we have. It looks like we've got, we're off by just a little bit. Looks like we have 19. It's just a little bit too low. Of course, we did round down, not a big surprise. Typically, that's what happens with Hamilton. So then we have to go ahead and divide by another number and see what happens, and so we could divide by, that kind of thing. But yeah, the fractional part of the quota, yeah, Hamilton does not redivide. I'm sorry, I take that back. Hamilton does not do an adjusted divisor method. Jefferson does that, and even Huntington Hill. A lot of them do, but Hamilton does not. He only looks at the decimal part of the fraction. So the largest decimal part, as I try to circle it here, is a 0.6. That's the one that gets an extra seat. So 2 plus 1 is 3. So 3, I'll circle it. Now this 3 stays at a 3. The west stays at a 12. The south stays at a 2. So that does add up to 20 because we just had to supply the extra seats. So that's how that one got reallocated into that kind of a situation. So we have the fact that the north, this is a terrible looking N, but it's supposed to represent north, got 2.6, and because it simply has the highest one, it rounds up to 3. And notice Webster would have done exactly the same thing. A lot of the time, these methods actually agree, and I don't know if we'd give you several different methods to do on the same data set. It's possible. I can't say I wouldn't do that, but anyway, we would naturally have rounded the 0.6 up to the 3. Anyway, 2.6 would become a 3, even with Webster. Webster seems to be the easiest method. I'm not sure why they didn't go for that one quite so much. I did find it very, very interesting, and I've got a lot of material from another book that I want to share with you another time. If you look at, well, it's 590 in my book. I'm not sure how the ebook does it, but they show the bias represented everything. And Jefferson went for the large states. Let's see if I can get, is there any more slides? Not really. I've got a little room here. But they said that Jefferson, you see a graph at the very end of the reading. And Jefferson, I'll just say Jeff for short, had these numbers that were going down at the bottom, which shows bias towards the large states. And they started way back in, I don't know, 1790, the very first one they did, all the way up to the current last one available, which was, I guess, 2000. And Jefferson was biased towards the larger states. So if you're a larger state like California, Jefferson's your man. But I'll try to put down large. I don't know why these things show up. I wish they wouldn't. And Adams turned out to be the highest one, biased towards the smaller states. Let me give kudos to Webster. Webster, I'll keep the bottom line as being perfectly unbiased. Now, he was never perfectly unbiased. That would be extremely difficult. But he stayed as close to being unbiased as possible. He was slightly biased towards the larger states at first, and then he snuck up, and now he's just slightly biased towards the small states. So small state bias, like the Electoral College, and large bias, and these are in terms of states. So I'll try to work the word state in here if my handwriting will withstand it. Let's see, the worst one was Adams. Of course, the one we've been talking a lot about is Hamilton. Hamilton does not make it to this list for some reason. I'm not quite sure why. But anyway, Adams, way up here, quite biased towards the small states, and it's been getting stronger. So there's Adams up here, and there's a couple of more. They also mention Dean and the Huntington Hill. I don't know what the Dean one is. I have to look that one up. But yeah, it doesn't bother to list the one we talked about. So anyway, there's bias through the years. If you'd like to take a look at that, if I could get a way of showing that on the screen, I would try to do that. I'm still working out a lot of things technologically. I'm trying to get to the point where I can write on the slides during the live lecture. That's what I always did in the live class lecture, was just to put it on the whiteboard and write all over it. And here I can only do it on the recorded lectures, and yet they would like me to do a lot of live lectures, so I'm obeying their commands, and yet the only one I can really write on is the recorded lectures. So frankly, that's my favorite. There were several other examples I could work on, a couple from the book that I'd like to do, and I have to recommend that you give it a try, that you try to work on the some of the odd number problems, especially towards the beginning of each section, and see if they will make any sense to you. There are answers to those, and I find them personally rather fascinating, but even if you don't happen to, the problems are not very difficult, and we do not have too many other examples for you, unfortunately. The other book we had 100 pages of material on this stuff, and here we only have about 20. and just a handful of examples. So if you want to, if you finished your WebAssign and maybe there's just too many multiple choices and you didn't really get enough experience with it, you want a little bit more experience, I have to recommend, this is just me stopping short of making it required because I can't really pick up, I'm not going to collect written homework. I've tried doing that last spring and it turned out to be a bit of a disaster. So you're kind of on your own, but I do have to highly recommend that you work on extra problems before the exam comes along. We did delay that. I believe it was on November 10 is our new day, so we have a little extra time. So between now and then, I do want to say a few more words about Chapter 8. Undoubtedly, we'll get into Chapter 6. Now, I just don't think there's going to be much room for Chapter 6 on the test. I haven't made an official